Hello. So now we will study the continuity theorem. This continuity theorem is based upon the conservation of mass principle. We know the conservation of mass is applicable, especially in the Newtonian physics, it is applicable. So in this case, we have a vessel. This is our vessel. This is our vessel. It's a closed vessel, and in this closed vessel, we have taken a test volume, closed test volume. Meaning, we will study only under this. Whatever is happening under this, we will study that. So this is our one layer, which is at the leftmost corner. This is A, B. We define the first layer, starting layer, and this is the exit layer, C, D. We are defining. So at this layer, let's define the velocity. So this layer have the cross section area A, let's say, and the velocity at this layer is V. Each and every particle is having the same velocity. That's what we are assuming here. So there will be multiple layers, and so when we go perpendicular to the cross section area, we are assuming each and every particle is having the same velocity when we go perpendicular to the cross section area. In future, in the next lectures, we will see why that will happen, because since there is no kinetic friction which is acting here between the layers, and in this chapter we call the kinetic friction as a viscous force. So since there is no viscous force acting between the different layers, so each and every layer will relatively be rest with respect to the layer. So since there is no kinetic friction, there is a static friction acting between these two particles. That's the thing. So there is a friction, but that friction is static, and that static friction is preventing the motion between these two particles. So if the motion between these two particles are not happening, then these two particles can only move with the same velocity, not the speed velocity. So that's why we always assume that any cross-section area which is perpendicular to the vessel will have the same velocity component for each and every particle. So these particles are moving with velocity v. So this layer, the location of this layer is at t is equals to t. Time is t at this point. So these particles are moving. Obviously, if we wait for some more time, these particles will move further. So after some dt time, meaning time becomes t plus dt. So when the time becomes t plus dt, this layer will move to the new location. Each and every particle onto this layer will move on to the next location. So this is the next location, A dash B dash. So this AB layer moved to the new location, which is A dash B dash. So this layer has moved the distance this much. And this distance, if you will calculate, since it's a very small time frame we are talking about, so we can assume, again one more assumption, we can assume that during that small time frame, the velocity is not changing appreciably. So if that is happening between this transition, we can assume the velocity remain constant. So if we can assume between this transition, the velocity remain constant, I can apply the formula S is equals to Vt, meaning acceleration is constant. So the displacement of the particle in dt time from this point to this point, the displacement can be written as V multiplied with dt. Because acceleration, we are assuming it's 0. Okay, so this layer has moved to this location. So you see, all these layers have moved to a new location. This is the new location. So this is the location of the layer at t is equals to t plus dt. So what will happen to the previous layers? The previous layers to the AB, this AB layer, the previous layers to the AB, previous cross-section, previous volume to the AB, that was not inside our test volume. During that time frame, that will come inside. So can I say this layer has moved to this location. So in this region, at t is equals to t plus dt time, in this region, this is the excess mass which has come inside. So in dt time, that much mass has come inside. So this was our test volume, and if there is no generator and extractor inside our test volume, what is generator? Generator is if something which can generate the mass, meaning if there is an inlet, somewhere there is an inlet. If there is an inlet, the mass can be the extra mass can put inside. So if there is no generator, there is no inlet, and there is no outlet in this. Only one inlet and only one outlet. So nothing can go out and nothing can go in. Everything which is coming in from this side has to go out from this side. So if this is the in, this will be the out, obviously. So first, we will want to calculate what is the rate of fluid which is coming inside, meaning dm by dt we want to calculate. How much mass has come inside in this dt time? Okay, so in this dt time, that much volume has come inside. If that much volume has come inside, so the volume inside dv, this dv, v is volume, not the velocity. For the velocity, I am taking the small v I am taking. So this is the volume. So the volume which come inside during that time frame, can I write this as A into V dt? So this is the width and this is the cross section area. Now if you see, I'm taking the same cross section area here, and again this is the assumption since this dt time is very small. So in dt time the displacement cover will be very small, the displacement will be very small, and if the displacement is very small, so even if the variable cross section area is there, we can assume that variation is not that large. So we can assume this cross section area will not change that much, except there is a cliff type of system, meaning if there is a system in which that kind of thing is happening. So when I was here and when I went there is a huge cross section area difference. So if there is smooth cross section area difference, we can assume that area remain constant there. So A is the cross section area and the V dt is the width. So the total volume which went inside in dt time becomes A V dt. This is dV. And if I want to calculate the total mass which went inside, so if you know, mass is density multiplied with volume. So the density of the fluid, this whole fluid I'm taking as rho. Majority of time density is assumed to be variable, but we take it constant. This density I'm taking at this point. So dm is taken as rho multiplied with dv. So dm becomes A V rho dt. Or we can say the dm by dt becomes A V rho. So this is the rate of flow of mass inside. That formula people should memorize actually. We can, at any point of time, we might have to use this formula. So this mass, this is the rate of mass which is going inside to any cross section area. A rho multiplied with B. And if in this formula, if you see, this is the mass which is going inside, and if there is no appreciable change in density happening, if the density at each and every point is constant, if density is constant, we can say the dV by dt, which is dm by dt divided by rho, will become AV. So this is the rate of flow of volume happening at any point of time, at any point of cross section area. So this is the rate of flow of mass and this is the rate of flow of volume. Any one of that formula you can memorize, other you can get by just multiplying it by density. So these formulas help us to understand the continuity theorem. So this is the rate we have calculated. The thing is, as I said earlier, the continuity theorem is nothing but the conservation of mass. And if density is constant, we can extend that principle to the conservation of volume principle. So in continuity theorem, the assumption is the mass slash volume of any test volume will always be constant. Within any test volume will always be constant. So whatever mass which is coming inside, the same mass has to go outside if the inside the test volume mass is to be constant. Or I can say, if in dt time dm mass is coming inside, then same mass within same time frame has to go outside. Or I can say the rate of flow of mass at inlet and the rate of flow of mass at the exit has to be same. And the rate of flow of mass, we already have a formula. So let's apply this principle, this thinking into the continuity theorem to derive the continuity theorem. So if I'll be having any cross section area or any cross section area which is having variable cross section, any vessel which is having variable cross section. So I've taken this as a variable cross section. In this case, here this area is A1 and here the area is A2. Here the velocity is V1 and here the velocity is V2. So it is changing. So this is my test volume. This is the inlet at the test volume. This is the outlet at the test volume. In between there is no inlet and there is no outlet. So rate of flow of mass inside at this point inlet and rate of flow of mass at the exit has to be same. Or I can say dm by dt at in has to be same as dm by dt at exit or out, you can say. So dm by dt, we have a formula for that. So in place of A, we have to write A1 because for the inlet this time the cross section area is A1, V1, and there might be rho 1, and the outlet will be A2, V2 and rho 2. So this becomes the continuity theorem. And if rho 1 is equals to rho 2, which is generally the case, if the density at the inlet and outlet is also same, this formula can be further extended into V1, A1, V1 is A2, V2. Generally, this is the formula we use because generally when the examiner gives the equation at board and JEE and NEET level, they don't give you that variable density, because in that case generally this question tends to become complicated. So this is the actual formula, and if you want to extend it to this one, if the density is constant, we can use in this format also. So this is our continuity theorem, either this one or this one, you can say. Okay. So I think if you understand this thing, continuity theorem, this was the test inside the test volume. We have calculated the rate of flow of mass. This formula we have to memorize every time, and then when we use this principle for the conservation of mass principle, we got continuity theorem. Okay. Thank you.